Hey guys, I just wanted to share with you a quick video here of how to draw electric field lines. So I've also shared this presentation with you so you can watch through it on your own as well, but sometimes it helps just to have someone explain it here. So first of all, let's talk about Michael Faraday for a second, a famous British scientist, mostly working in the 1800s there. And he's one of the first to discuss this idea of fields or invisible lines of force, he called them. And at first he did it with magnetism, but it was later applied to both electricity and gravity. Also, he invented the marshmallow. Well, that's not actually true, but anyway. Okay, so here's a picture of a field. So what is this field that is drawn right here? Let me get my pointer out. So an electric field is a force field that surrounds a charged particle. So here we have a negatively charged particle, and here we have a positively charged particle. So we draw these lines of force. That's what these lines represent, are forces on other charged particles. So this is how Michael Faraday finally answered a question that bothered Newton, which was how can this charge affect that charge or another charge that's sitting up here without touching them? So you imagine surrounding these magnetic things or gravitational things or charged things were lines of force surrounding them that only really mattered when you put some other charge there or some other mass there. So an electric field, by the way, is a vector. That means it's got magnitude and direction. So how much and which way. The equation that defines an electric field is right here. Capital E stands for electric field, and it's the force per charge. So think about this as kind of like the electric version of acceleration, right? Acceleration, Newton's second law, was the force per mass. So this is the force per charge. So the units, by the way, since it's force per charge, are newtons per coulomb, and we have not renamed that, so there is no special name for that named after a scientist at all. Look at these two drawings of field lines here around single charges, a single positive charge and a single negative charge. So if you look here, you'll see the arrows point away from the positive one and towards the negative one, because remember, electrical forces, unlike gravity, which can attract or repel. So we had to pick a way to think about it. Are we going to think about it from the positive charges point of view or the negative charges point of view? So we chose the positive. So these arrows indicate the direction of force on what we call a positive test charge. What's a positive test charge? Think of it like a proton. It's going to be something with a positive charge that is so small that it doesn't really influence the other thing there. So if you put a little proton right here in this spot, it would follow this line. It'd be pushed this way and zip, it would accelerate that way. Or if you put it over here, zip, it would accelerate that way. Or if you took your little positive test charge and put it right here, it would be attracted to that negative charge. Since opposites attract, and zip, it would be pulled in there. So what if you got an electron? Well, just remember these lines of force get switched in their direction if you're talking about something negatively charged, because these lines are showing the direction of force on a positively charged object. So again, what are these lines? They're not a material substance. The field isn't there in the sense of it's not something material. They represent forces that are there. And that effect is real. So we can consider the field real. One thing you want to consider here is the denser the lines are, the stronger the field. You want to be careful about saying the more lines there are. Because look, however many lines there are right there, there's the same amount when I'm close to the charge as when I'm farther away out here. But when I'm close to the charge, the lines are denser, meaning the field is stronger. So line density is what gives you the strength of the field. This is a very common diagram that you should memorize, which is between two different charges. So notice we get this weird like alien face or sort of watermelon shape, whatever you want to call it. So if we put a positive test charge right here, it's going to be pushed by the positive one and attracted by the negative one. But since it's closer to the positive one, that push away is going to dominate it first until it gets further and further away. And then the pull starts to have more and more of an effect because it's getting further from the positive one. And at a certain point, the pull of the negative one will overtake the push of the positive one and pull it back in there. These lines, by the way, extend out to infinity theoretically, although they'd be very weak, basically to the point of zero out there. So what this is a little example that they put a charged object here and they put metal in here that interacted with the electric field. And so you can see here actual lines that let you actually see the electric field there. And here's this alien face or watermelon, whatever you want to call it, where the positive one is here, and whoop, you get pushed and then pulled over into the negative one. Here's another good one to know, two like charges. So in this case, they're two positives. You can't see the direction of the arrow. First, you get pushed away from this one, and then you zip up there away from that one. So, and down here, it's kind of like a double waterfall. You get pushed away from one, and then eventually both of them straight down or straight up. This is an interesting electric field that we're going to see a bunch this unit and the next unit, which is in between two parallel plates, we call it. So right here, you just be pushed straight across away from the positive and towards the negative. So the lines go straight across there. Although notice on the ends, we get a little bit of that fringing effect because the ends become a bit more like there's just two oppositely charged point particles there. We'll talk more about that later. Here's something very interesting. Here's a positive metal plate and a negatively charged sphere. And look, there's no lines in there. So there's no electric field inside a conductor. That is very important. That is called a Faraday cage. So here's a gentleman with a big, probably Tesla coil shocking these two shopping carts. He's inside a conductor and there's actually no field there. So that's one thing you got to remember. Inside a conductor, like this metal box, there's no electric field. Even if you're shocking the heck out of it there, and you've got a meter to measure the electric field, you're not going to measure anything. Faraday was the first to notice this, by the way, and that's why we call it a Faraday cage. So why isn't there any electric field inside? Well, it's because all these charges, let's say you dump a bunch of electrons on here, all those electrons will be pushing on each other, and they will push each other and move each other until all of them move into a position, which this happens almost instantaneously, that they come into a balance. So eventually they'll spread out until they're all pushing on each other with equal force. And if we have no net force, then according to the equation of the electric field, we'll have no net field inside the metal conductor there. You can watch this video on your own in the Google Slides if you want to. I'm not going to play it here. One last thing we got to go over is another equation for electric field. So let's say this big charge, big Q here, is going to be affecting some smaller charge, little q here. And we want to know this distance r away right here. What is the electric field at that point? Well, we know one way we can find it is by taking the force on this particle, divide it by its charge there. That's the definition of electric field. But there's another way to find it based upon this charge that's creating it. So here's how we find it. Remember, electric field is defined as the force per charge. How do we find this force? Well, we can use Coulomb's law, which says K times Q1, which we'll use the big Q, times Q2, the little q, divided by the distance between them squared. All of that is the force. So what's this Q? It's this Q right here. Notice there's a Q here and a little q here, so they cancel out. So another equation for electric field is K times Q that's creating the field divided by the distance from it squared. We had a similar equation like this, if you remember from AP1, where this would be the gravitational field strength created by a mass. It's exactly the same, except we swap mass for charge there. So again, what is this one? I call this version right here, it's not only the definition of electric field, but I call it the experiencer equation, because this little charge is experiencing the field. This would be kind of like the apple. And I call this equation over here the creator equation, because this big Q right here, it's creating the electric field that the other one's experiencing. You might say, well, doesn't the little q exert a force on it and create an electric field? Yes, it does. But if this is a big charge and this is a little charge, and this is a big mass and a little mass, it might not actually be pushed that much overall. So that is the basics of electric field, and you should be ready for the following assignments. And let me escape out of here and stop the video.